Okay, we're going to do some more of sections 5.4 and 5.5, talking about logarithmic functions. And I wanted to talk about the properties of logarithms next here. I have this sheet on Blackboard for you guys. I don't think I had it in the notes that I had posted, but I included that later. So on this sheet, and be sure to try to print that if you can, but on this sheet here is our laws of exponents and laws of logarithms. Okay, now all this is in the book. I just kind of made it on a sheet so it's convenient for us to refer to here. So on one side of the sheet, I've got our laws of exponents, and now you guys already have all these laws in the notes from section 5.3. So here's those laws of exponents again. I would like us to focus on the laws of logarithms. Okay. So there are 8 laws of logarithms that I feel are important to know. Law 1 says that if you have a single logarithm and you're multiplying the inner terms, you can split that into 2 logarithms where the operation is adding. Okay. Law 2, if you got a single logarithm and you're dividing the inner terms, you can split that into 2 logarithms that are being subtracted. Law 3 is essentially saying that powers can come out of logarithms. Okay, this power of r can come out in front and be treated as a multiplier. Law 4 says that log base anything, doesn't matter what the base is, log base anything of 1 is 0. Okay. So like log base 2 of 1 is 0, log base 5 of 1 is 0, log base e of 1 is 0. Log base anything of 1 is always 0. Now over here I've kind of got a calculation showing where that comes from. If I let y be equal to log base a of 1 and then apply the definition to rewrite that into exponential form, I've got 1 equal a to the y. Well, the only possible value for y to make this statement be true is that y has to be 0, right? We know that anything to the 0 power is 1. Y is 0. Now y is representing this logarithm, so that's where this 0 is coming from. Law 5 is saying that whenever the base and the input number are the same, you always get 1. Okay, log base a of a is 1. Now, to see where that's coming from, if I let log base a of a be equal to y, and then I apply the definition for rewriting that into exponential form, I have a equals a to the y. Well, the only possible value for y to make this statement be true is y has to be 1, right? A to the first is a. If y is any other number, you're not going to have a true statement here. So that's where the 1 is coming from. Laws 6 and 7 kind of go hand in hand by understanding that an exponential and a logarithm are inverses of each other. Okay, if I have y equal log base a of x and y equal a to the x, like those two functions are inverses of each other. Now remember that when we were talking about inverses, the way to check if two functions are inverses of each other is through function composition. Okay, plug each function into the other and check that you get plain old x. So if I let f of x be equal to log base a of x and g of x be equal to a to the x, f composed g of x is x. Now if I plug a to the x into this logarithm here, I've got log base a of a to the x, which is just x. Okay, so that's where law 6 is coming from. Now, g composed f of x is also x, because these are inverses of each other. So if I plug this logarithm into the power here, I'm going to have a to the power log base a of x, and that's just equal to x. Right? So here's where law 7 is coming from. So to me, laws 6 and 7 just come from simply knowing that a logarithm and an exponential are inverses of each other, which is one of the key things for talking about logarithms. Law 8 is sometimes called the change of base formula. Sometimes we want to change the base to make it a new base. So if the current base is base A and I want to make the new base be base B, here would be the change of base formula that allows me to change the base. Okay, and I've got kind of a calculation showing where that's coming from. You can look at that if you want. Also on this sheet, I've got some important statements to know, 4 of them. So the first one we were using in section 5.3 when we were solving an exponential. If you have the same base on the exponential, you can remove the base and set the powers equal. And so we've used that a couple of times, including using it for finding values of logarithms after we had applied the definition. Important statement number 2 is the definition of a logarithm. That I've mentioned a couple of times now. That is the most important part of logarithms. You got to know the definition. Okay, so I would maybe put a big star by that one. Okay. Statement number 3 is also the definition of a logarithm, but for when you have base e. Well, it doesn't matter what the base is, whether it's base 2 or base e or anything. The definition is going to apply here. So there's really nothing new in statement number 3. I'm just using the same definition for when we have the the special number e there. Now the fourth statement is a new one, and it's saying that if you have a logarithmic equation and you've got the same base on both sides, you can remove the logarithmic notation and set the inner terms to be equal. Okay, so m is equal to n. Now this is an if and only if, so I can read this beginning to end or end to beginning. Okay, and in other words, if I have an equation m equal n that had no logarithms at all in it, I could take log base a of both sides, and we're going to want to do that sometimes where we have an equation, we're solving for x, there was no logarithms there to begin with, but the only way to solve for x is to be incorporating logarithms into the calculation. Okay. A lot of important stuff on this sheet, so be sure that you've printed this and looked it over. And now that we've gone over that, I want us to maybe take a look at some examples now. In this first example, I've got a couple parts. I have a single logarithm, and I want us to write the logarithm as the sum or difference of logarithms, and then give the answers without exponents. That's how the book is going to want it also. So part A, I've got log base 5 of x times the square root of x squared plus 1. Well, law 1 on that sheet that I just went over said that if you have a single logarithm and you're multiplying the inner terms, you can split that into 2 logarithms that are going to be added together. Okay, so that's where this next line is coming from. Now, powers can come out of logarithms. That's law 3 on that sheet. And if I had the square root of x, square root of x is the same as x to the 1/2. Okay, so if I have the square root of x squared plus 1, that would be the same as x squared plus 1 to the 1/2 power. And that's how I'd want to look at this second part here, because powers can come out of logarithms. Like I can bring out that power of 1/2 in front of that second logarithm. The first one I'll just keep as is. I got log base 5 of x, and then plus 1/2 times log base 5 of x squared plus 1. Now, I can't distribute a logarithmic notation into terms if I'm adding or subtracting. Okay, some students want to do that, and that would be a wrong move there. Okay, so what we have circled here is as simplified as we can get it, in other words. Part B, again, I want to simplify. So I've got a single logarithm. Now there is no base. Remember that is base 10 if I don't have the base indicated. Of course, the laws apply to all logarithms regardless of the base. And so I see that I'm dividing the inner terms here. So I'm going to want to begin the calculation by using law 2 on that sheet that I gave you, where I can split the logarithm into 2 logarithms, and I'll be subtracting those expressions. All right. Now, the last thing that I want to do is I want to bring the powers in front of the logarithmic notation. The cubed root of 2 minus 5x, that would be the same as 2 minus 5x to the 1/3 power. So that power of 1/3 can come in front of the logarithm. Of course, the power of 2 can come in front of the logarithm here on that other term. And I'm looking at 1/3 log of 2 minus 5x minus 2 log x. That would be as simplified as I can get it. Part C, I see that I'm dividing inner terms again, but I've got the square root going on here, and the square root of x is the same as x to the 1/2, right? And so this radical here, I'd want to look at this as an exponential form, an exponent form, where I've got a power of 1/2 that can come in front of the logarithm. Okay, so after I've done that, now I can use law 2, where I split the single logarithm into 2 logarithms, and I'll be subtracting those logarithms. Okay, so I'll have the ln of x cubed minus the ln of x plus 3 to the 5th. Powers can come out of logarithms, so I pulled out that power of 3 and I pulled out that power of 5. And the last thing that I could do is distribute the 1/2 into these terms here. Of course, I want 1/2 times the whole thing. So the brackets that you see are a necessary thing, you know, that I've got written there, and then I've distributed at the end to get my answer. Here's some other problems. So let's go the other way. What if we had a bunch of logarithms and we want to kind of condense it all into a single logarithm? Again, we're using the laws on the sheet that we've went over. So part A, I've got log base a of 7 plus 4 times log base a of 3. Well, before I take care of adding here, I know that from law 3 on that sheet, powers can come out of logarithms. So, and that power can be treated as a multiple. Well, I could also look at it as if I have a multiple, I can pull that number back inside the logarithm so that it's a power of the inner part. And that's what I'm going to want to do to begin this problem here. This 4, I'm going to pull that inside of the logarithm so that it's a power of 3. 3 to the 4th is 81. And so now I'm looking at log base a of 7 plus log base a of 81. I don't have any multipliers. I've already taken care of that, right? So now I can use law 1 on the sheet where I get my single logarithm by multiplying the inner terms. 7 times 81 is 567, and so I've got log base a of 567, and there's my single logarithm there. Part B, 2/3 ln 8 minus ln of 3 to the 4th minus 8. Okay, well, 2/3 is a multiplier, so again I'll want to use law 3, where I can pull that inside the logarithm so that it's the power of the inner part. 8 to the 2/3, I'm going to figure that out in the next line here. 3 to the 4th, well, we've already said that's 81, and 81 minus 8 is 73. So now 8 to the 2/3, using law 8 on the exponential side of that sheet, 8 to the 2/3 would be the same thing as the cubed root of 8 squared. Well, the cubed root of 8 is 2, and 2 squared is 4. So 8 to the 2/3, that'd be 4. Of course, I still have the ln notation here. And now I'm looking at ln 4 minus ln 73. I'm ready to get my single logarithm by dividing the inner terms. I'm using law 2. So the ln of 4 over 73 would be my answer. There's my single logarithm there. Okay, part C. I've got base 6 on all these. Let me take care of the 3 and the 1/2. We'll pull those multipliers inside so that they're powers of the inner part, and I've done that here. Of course, I'm using radical notation. X minus 1 to the 1/2, that's the same as the square root of x minus 1 using radicals. Okay, I don't have any other multipliers, so I think we could probably just go right to the answer here. The first 3 terms I'm adding, And so using law 1, I'm going to be multiplying the inner parts. I'm going to have x cubed times 4 times the square root of x minus 1. You see that up top here. Now I'm subtracting log base 6 of 5. Since I'm subtracting, I can use law 2 where I divide these inner terms here. I'm going to be dividing by 5 to complete the problem. Okay, so there's my single logarithm. I can circle that, and that'd be my answer.